Welcome to the webinar. My name is Pravin, and I have a brief background in mechanical engineering as an education, and then working now about 12 years in composites industry. Mainly started with satellite and launch vehicle structures, and now with the automation side of composites manufacturing with thermosets and thermoplastics. Um, and in this webinar, what we wanted to focus on was with the how we can revolutionize filament winding. And I'll talk through this process. So we have built out steps um, like what we will cover. So let's get started. So as a structure, what I'm proposing is that we go through just going through what we usually know, and I would assume here everybody's aware what is composites, and what is basically filament winding process. That is what I would assume would have interested you to begin with, like in the topic, and now how it is improving now as a process. And we will go towards how filament winding resulted in AFP access and the new phase of filament winding as we see from AFP point of view that we want to bring here. Yeah. And later on, there will be also hands-on project that will be shared. So I'll come to that in the middle portion of the talk, and later I'll focus more on the applications that this potential brings, and the benefit. And we will wrap it up with Q&A towards the end. Let's get in. So filament winding, as we know, I would assume I don't know a time where there was no filament winding, but from what I could identify from literature, when composites started to getting used into the industry space side as well, about 1960s, where there is material source, which is what we call bobbin, and that is where the material is held with some sort of braking mechanism that is making sure that it's not getting loose and opening up. And then somebody manually draws it through a bunch of hoops where there's a place where there is a tension getting measured along the way. And then there is like an eye towards the end that is bringing it towards the mandrel. And the mandrel is what is driving the fiber. So somebody has to manually tie the continuous fiber toe or tape or toe preg at the beginning, and then the mandrel start to rotate, and that is what draws the fiber in the tension. And what we assume with as a very fundamental principle of the process is, because continuous fiber held in tension goes in a straight line, and based on that, a logic is programmed to be able to wind either a cylindrical, conical mandrel, usually and very conventionally circular bodies, or axisymmetric mainly, without any negative curvatures. So mostly positive curvature is what is allowed, because as it goes in under negative curvature, due to the tension, the fiber will not go in that dip or in the negative curvature area, and then you will have bridging. So that has enabled filament winding to be one of the, I would assume, the biggest process that I know that is used out there, like along with pultrusion. And the process, to my knowledge, or what best in industry practices is focused towards thermoset and dry fibers that it is able to wind. Usually the eye is, as you can see, is kept far away from the mandrel position, so it's not able to impart any heat. So there is very little to no evidence of thermoplastic usage of this process. The key feature, what I feel filament winding has, is you are able to bring multiple strands of toes to the uh, winding eye, and it could be God knows how many, and then you can just find around, so you can scale the process like hugely without losing anything. And that is what was, I would say, since 1960s to even today, is what is known very massively the process is. And as we now move forward, um, that is what I would say 1980s, 1990s, when we see the development of AFP. And what fundamentally different what AFP does is allow you to do those negative curvatures, and adds a layer of like, oh, you can start and stop without a manual intervention. So it has, as you can see, there is an additional driver that is going to push the fiber forward, and then there is for holding the fiber at a certain position and cutting it. So there is a what we call clamp cut start, um, as a CCS unit that is added to the basically the filament winding setup. And now what you have is essentially AFP. And once again, you can do that for individual toes, and you have a ATL AFP system. The key benefit of this process, I believe, comes from like, because you're able to, you're not restricted not by the geometry that is driving the fiber. You can start and stop anywhere. You are more intelligent and smart about how you're able to place fiber, but it does make the system very complex. Sorry. And that is what is also listed here as, that's what start to make the process really expensive. So as I've highlighted here, it's usually uh, bigger AFP systems that we know easily. You're talking in few million range. They are very good at what they do, so they are able to do fiber almost in any angle which is physically allowed. They can do to be placed. They can allow for fiber in plane steering, once again within the physics limit. And they are very precise in placement compared to filament winding, which is more reliant on tension than actual position. So yeah, so with this benefits, but there is a drawback there. This is kind of what we see that as the advanced stage from the filament winding. And then we come to what I would call like 2020s, so almost now, and where we see more and more compact AFP systems. We like to call them AFP XS for extra small systems. And this AFP XS systems out there, they are very good. They basically do the same function as the bigger AFP heads, but now they can, instead of getting built ground up as big giant machines, they are simply leveraging the existing robotics that is already installed for other purposes, or just normal robots which are very accessible, and then can convert those robots into AFP machines. They have the similar features of being able to do thermoset, thermoplastic, dry fiber as AFP machines, but then they cost similar to winding system despite having the complexity. And this basically what we call is the advancement from like the evolution of the process. So this is the landscape. What this compact size also enables is, now as the cost parity has been achieved, there is a very good sorry there is very good possibility to use the same system for winding as well. And that is what what we like to call AFP winding. So now you're winding or trying to create kind of wound shapes, what you would do otherwise with filament winding as well. But now you're no longer limited to just the positive curvature. You can do a lot more. So, and adding the same value So you're able to go really fast. You can scale the process to big scale, but have all the benefits that other AFP brings without adding to the cost. And that's what the revolution we believe this brings. Um, and we'll uh, deep dive into the AFP winding step. So, what we understood, there is a filament winding. It's been developed for long. It's very standard process. Um, there comes along AFP and then now compact AFPs. And now these compact AFPs are able to be used for winding units. And so the first question, and we'll dive into these three questions now: why AFP winding? What differentiates them? And how to actually use this compact system for winding. So let's get in. So why AFP winding? Um, as we can see, you're able to do selective placement. So if I'm able to zoom in here, as you can see in the video, um, there is uh, I have a dome here, but I'm not going all around to be able to reinforce, but I'm just doing the dome reinforcement basically. So instead of going complete back and forth, I'm only reinforcing what I need to reinforce. So I'm basically leaving out the cylindrical portion here for, and I'm able to achieve what we would call a selective reinforcement of the dome. The one of the kind of I think a dream of a composite engineer is to align their fiber to the stresses that they have seen in their simulation. And this is basically what also the AFP winding enables. Because the systems are quite compact, you can use multiple narrow tapes or single narrow tape, and then actually bring, based on your stress and FEA analysis, what the fiber orientation should be. And you can actually also analyze if the manufacturing process would enable the manufacturing to be able to do it, because it will tell you if it is reaching a steering limit. um, this is like it's a big deal, mostly where performance is the key. In aerospace, this has been one of the very sought after um, feature that let's say Airbus or Boeing would want to have in their parts. Just it's not well at the moment accessible with the bigger systems, and that's the key benefit that this brings in. um, then we have thermoplastic here. Because the, as we can go actually to previous slide, but the compaction roller where it is touching the mandrel is always touching the mandrel. There can be the heat source that is placed, and what essentially you can do is thermoplastic welding, or what we call it thermoplastic placement. In this case, it will be thermoplastic winding. So you're able to create thermoplastic winding very well with the system, which basically enables sustainable winding, which is, to my knowledge, at the moment not possible with conventional winding approaches. And this basically opens up a complete new segment of application that can be welded, repaired, um, and I think I don't need to go into the thermoplastic bandwagon, but yeah, AFP winding enables that use case. Let's look into few more, like why I would not do winding and why would I do AFP winding. What I have here is a foldable. Sorry, I think there's a mistake in the name. This is a boom that is deployable boom for space structure. Um, it's a very unconventional shape, as you can see, but because this can be folded, and as you can see, there's a NASA logo and that's developed by NASA for deploying the large solar sails, as they call it. And this is not possible with conventional winding approaches because, once again, there's a negative curvature. And right now, to my knowledge, how this was manufactured was just by hand. Some people forming it and some people welding it. You don't know, you're not sure about the quality, but then you hope for the best, and then you are able to get to this. So yeah, overall there is a very good application. So once you have negative curvature, you're able to see, like, yeah, I need to have AFP winding. This is one of the application that I saw in one of the paper. I should put that citation here. um, this is very unique, where AFPs as a system are usually considered to do very large structures, but as you're able to use this compact AFPs, you can use them in conjunction with like some what we call like a turning points. Then you can create very compact, and this is like a thermoplastic bracket here that you can create with almost, I would say, 60% fiber volume fraction, where the fibers are completely aligned to the load where it will be coming from, and it will be guiding, and there is almost no kind of discontinuity in the fiber. It's almost continuous. Actually, you can do complete continuous here, but discontinuity really helps with the speed of the process. So, and this is, I think, one of the very cool applications that you start to think, oh yeah, there is a lot of compact structures also that can benefit with the same winding approach, just with the enhanced mold design here. And this is one of the beloved application from space. Space fairings are built similar to, like, there's a skin and then there are stiffeners that used to be aluminum machined to begin with. Then they started to get made from composites and sandwich structures. And now the recent evolution of them is basically isograde. So there's a skin, and then inside there's basically grids that are made from this continuous carbon fiber toes that are placed in the wounded fashion, and basically you're able to create a gridded structure that you can post bond, or you can first mount this, and then on top of this you can place the skin to be held, and it gives still like a very good aerodynamics, and then the stiffness that you need in the for the vibration loads that you're going to experience during the launch. So this, if you would want to do it with conventional winding, you would need a special type of mold which has grooves, and then the winding will fill up the grooves. So it's not completely impossible, but I would say you can do much more with this approach, where if you want to change in the design, you don't have to change the mold because it's done directly on a cylindrical mold directly. So I think by this point, my goal is to show off some of these applications that are um, shines the AFP winding and why it's necessary compared to the conventional winding, which is great for many of the purposes. But AFP winding enables all of this. Um, so if we try to compare the benefits, so you really need to choose depending on what is the industry application. And this is why I put this slide here as, like, what is the differentiator? When should you choose AFP winding and when should I choose a filament winding? When I have a product that is okay with fiber misalignments, okay with a bit of a weight extra, and the geometry is more with just positive curvatures, I think filament winding is the answer. But if you have the same budget, and if you can be okay with slightly less production rate, so let's say from 10,000 to you're thinking 8,000, so not huge reduction, then you can think of AFP winding as a solution. It works with the same set of material that you would use for filament winding. It can do everything that filament winding does, but the addition comes with the able to do this, what I like to call high value structures, where you're able to optimize even further the same structure, and you go into the nitty gritty of like, okay, how things are going to get placed. And this is what I believe is the key differentiator from AFP winding to filament winding. In addition to this, there are definitely the material side of it. So if there is something that you are trying to create from sustainability point of view, I would by default nowadays go for AFP winding because of its ability to move around with different materials and work with those. So for thermoplastics, I would usually just would recommend thinking about AFP winding. But if it is okay, and you're okay planning to have a separate process with some RTM or infusion style later, I think there is a possibility also with sustainability with filament winding. But these are, I would say, my main decider. Um, with this, I think as a differentiator, bit gone out of the way. Um, Now I want you to focus on, like, if you have decided, okay, I'm gonna go with AFP winding, what I need to do, how should I get started, and how would I go towards making the first part, and then scaling that part's manufacturing process. So first thing first, you need to kind of configure the system. So what we see here, I'll pause this video just for a bit. Let's say here, so I can use this as a reference to talk about things. So here is the material that is held, and let's say if we use if you're using a dry material or thermoset material, um, the heater that is here, that should be sufficient. That is, at the moment it is IR heater, it can be brought much closer, and the system is able to process and work very well with both of those. In case of just if you're planning to use just geodesic winding, you don't even need the heater in most of the cases. But as you start to think thermoplastic, the heating element is what you have to really think. And there are three different options here. Flash lamp, which is basically lasers, safe lasers, you can call them, so you can work around them. Then lasers themselves just need to have close enclosures, you can't be near them. And then thirdly, you would have the other hot gas and a torch, basically. Those are less controllable. So, but for low cost applications, once again, the bonding quality, how good you would want them. So, and there could be all three different type of heater that can be mounted to this system, what is seen. um, so basically material and heat almost go together. um, Now let's say I've decided, okay, I'm going to use a low temperature thermoplastic material. For me, a flash lamp is good enough. Then I need to start to think, okay, if I'm gonna use like a flash lamp with some thermoplastics, my mold cannot be anything else but metal, or of something that is able to take more temperature. So some soluble molds can be there, sand molds could be there, also metal mold could be there. If you want to have, once again, then it cure then and there, then it would be also good to think if you want to have additional source of heat that is directed towards the mantle. So just in this case here, there is just a flat plate, but this flat plate could be heated. So the same thing with the mantle as well. the mandrel could be heated, or you can have additional IR lamps focusing on it to minimize the what I would call the temperature delta during the process. So the temperature delta in the environment to the actual processing temperature, the better part is going to come out, less thermal stresses. Yeah. So let's say now we know my material, my heat, my mandrel and mold is there. Alignment usually, I think it's once you are doing it, like setting up the machine. After that, it should not matter that much. But yeah, then going to the program. So I have actually a surprise for all the audience in this webinar. Uh, so for programming, so all the examples I shown to this point, there are AdPath programs I have made that will be sent along with the video recording. So you can just open them up in your AdPath and run it and make changes and play with it. So we'll get to that step next. So I'll talk about the programming part just right after this slide. But let's go through the full process before we just look into the program side. During the operation, it is very critical. So it's very critical to capture all the process parameters that you are doing using during a process. So it's not only the parameters that you are inputting into the program, but what actually is happening at the real time in the process. So with AFP, this is one of the other key advantages, that because you have a lot of sensors that you can attach, and the head or the compaction roller is so close, and it's always at very close proximity of the mandrel, you're capturing data almost in real time. And that is a huge plus, once again, for quality control. And then you being able to tell, oh, if my process is going wrong, where could it be? Because you have the data to prove it and capture it and also alert it. And that makes this really highly automated process. So if your product is coming out with all the right process parameter, you can be almost close to sure that, okay, I got a part that should be like according to what I planned. With thermoplastics or mostly thermosets, you really need to think of, I will be curing the system or my thermoset material, or I will be doing some injection. So you need to really think of, like, I have to demold it. So and then with thermoplastic, you have to think of, like, okay, am I getting the full bonding already, or do I need to still heat it up later to achieve the full bonding? In thermoplastic, there are strategies, so in situ consolidation and post cure, and that could be depending on at what speed you decide to run the process. Just a sec. So overall, at this point, if you have decided, okay, I'm just gonna use autoclave for curing my thermoset component, and it goes in either the oven or autoclave depending on the material, or if it is just dry, and then some infusion process, and then just left for curing. And with thermoplastic, either you have a thermal blanket to help with the post cure, and high temperature vacuum bag, once again, to assist with the post cure. Once all the basics here kind of checks out really well, then you are in the position of scaling up the process. So I usually recommend to start with the single toe approach, and then you can either increase the scaling by changing the width if the product allows, or having more number of toes, which is slightly expensive but still within reason. For complex shapes, that is the approach that we would usually go for. And then you would want to have a mandrel that is able to rotate really fast. so that it is able to match the processing speeds. And yeah, I think those are the three key, I think, parameters that you would definitely. Heat and the material is the big part of that mix. But because those decisions are already taken in a way, once you start to, like, depending on the structural requirement of the part, there is the production rate that you are able to achieve. Other than buying more system, it's just as we're focusing on like one system and how we would be able to scale. Yeah, but before now, I think we got an idea before even having an AFP winding system. If we were to run it, like what parameters I'm looking for and what my system needs to have, what scale I might be able to achieve. So I think this slide was added just to give that idea.
Praveen,
Yeah,
before we go next, we have one question.
sorry,
What
please
is
go ahead.
the what is the maximum speed for AFP winding?
It's a function of mandrel, basically. So AFP is not limited on its own by winding, because here either it's a function of material, or it's a function of mandrel speed. So let's say if we are using thermoplastic material and you want to do in situ consolidation, which is when you go the slowest, because you want to heat the material, allow enough time for it to be compressed and cool down well enough, so that is what will decide the speed. And let's say when we are winding thermosets, to be honest, if your mandrel can rotate at few meter per second, be it, it should not be a problem. uh, Usually that is what I found the limiting factor to be, is the mandrel speed. The tool, the robot is able to go at 2 meter per second, and then the tool is not limited usually by that, because once again with AFP winding, it's all digitally servo controlled, so they are very fast to respond to any change in speed or things like that. But really, thank you for the question. I think that was very good question there. Yeah, so let's go to the planning. So as I promised in the program stage, let's look at actually how the planning for such system. um, yeah, so in the anticipation for the thing, of the webinar, I planned this is once again very simple tank geometry that you would plan otherwise. um, I can actually open other few ones as well. uh, so let's start it from the beginning. Mm, I will just clear this up. Let me do this. Unplan. Okay. And then I can ask unhide all. Yeah. So this is basically the geometry that I have imported from a file. It usually comes into pieces. As you can see, there are multiple pieces here that I have selected. And I have created the position of this axis at some location here based on the axis that I have created at the chuck. So once I know with respect or calibrated where my chuck is located, I have inputted this value. Uh, and I have made sure that it is linked to my external axis 1. Um, then I'm planning to do the winding onto these 3 surfaces. So as you can see, I've selected this surface, and the surface here. And then I have the boundary surface. So I have like a small eye section here that I'm leaving out. I don't have to leave it out, but I'm leaving out. And then I'm leaving out a small similar eye portion here, because I want the winding to be symmetric for this particular domain. And I can see here I have defined my 0 degree along the axis. So I can define just by clicking here. Let's do that actually. So I can go define and I can select. So I just have to make sure I do the definition of this axis at the beginning of my uh, cylinder position. So there we go. So I selected the center, and now I'll try to select the center at the other end. That's my 0, and I try to find my 90. Um, yeah, there we go. So we have defined my 0 and 90. Sorry for my choppy mouse work there. So, and from here, I have selected the continuous winding approach. This is for cylindrical tank with dome. If I had something else, I would have selected different modes. Now there's also an option to write your own script as well. And here, either you can input the values where we want it to be. So the length of the diameter at the section where we have the 0 degree and 90 degree defined. So at this section, we can either measure it like so, or we can just input the number that we know from our CAD. The length here is the length from this section to this section. We can once again measure it, or we can input it from our CAD. Here, what I have here is I'm doing run for one circuit, and this is usually if I put 0, then it will do the complete coverage. Right now I'm just focused on showcasing, let's say I do 2 circuits, and then I have the angle defined here, which is 30. We can do a bit more optimistic, or let's say 35. Very unconventional angle. Never seen 35 in a layup. Okay, but with these parameters, with my toe thickness, assuming I'm using a 1/2 inch wide tape, yeah, I'm planning this. So as I start to see at the top here, it's able to tell me the values it is generating. I can read it out. It's quite small text. So I got the winding angles in left and right for 36 and 34.5-ish. And I got I should get a pattern number and a friction value as well that it calculates. Okay. So now I have this. Let me do the hiding of this. Here is where we see the ply and the circuits that we have now generated. What we see here as well, like how long is the length of each circuit of the tape, basically, that will be used, and how long, based on the speed and the accelerations that we have inputted, it should take. Okay, now we have refreshed everything. Let's play this out. So as you can see, my main goal usually here is to see, I'm going really fast. I can go slow a bit, but I want to see if there is going to be any collision. I also want to see how much I'm pressing. I think I'm pressing the right amount, but I can press more, less, and things like that. Yeah, I think there is like another things that I'm able to find out a lot more just from here. I can extract the path, and so, like, a lot of what you are able to do already in AdPath is all possible with the AFP winding. I wanted to quickly also show uh, the isogrid structure. I will not plan this. I have just planned it the same way. Um, but yeah, this I believe is done a bit differently than the previous structure that I shown. But yeah, this showcases like what you can plan. So this one, For planning the ISO grid, I did not use the winding feature that comes built in with that path, but I generated these paths based on my some knowledge, let's say. So I basically drew these curves when I was making the CAD. So I just drew one curve, and then I just brought those curves as along with my CAD. This could be done also directly from the FEA software. And I was like, okay, as you can see, there's just a helix curve that is drawn along the geometry. And once we choose custom curves, it does not matter what angle we put, because it's the angle of the curve that we have already in here. Depends how many layers we want, so we can include more layers. And yeah, that's we have it. I think just to play around with what we have here, let's put a 10 millimeter tape and let's see what it does. So yeah, I think now it's planning all the frames for isogrid structure. But now instead of for a 1/4 inch, it's for a 10 millimeter white tape. Let's say I found some tape that is 10 millimeter. So I think this is once again on top of the winding, you're able to draw your own custom paths, and this enables you to do pretty much anything that you can think. Either you can write a script for these paths, or you can just draw them in the CAD where you're creating the sketch for the mold or the mandrel. Okay, think we are almost done here. Let's hope for it to draw. Yeah, there we have it. Let's increase the speed. Oh, I have my orientation flipped a bit, so let's fix that. Okay. Let's see. Now again. Okay. I think, yeah, so I was able to fix. I saw that the robot was hitting limits there. And now we have all the long passes drawn after the, let's say, the boundary passes. And yeah, I think here we have the grids now drawn, and we can continue drawing them in whichever fashion we like. But yeah, I think, as I said, these files will be available and sent along uh, with the webinar recording. So I think this is what I wanted to actually talk mainly about. That you can, depending on your structural requirement, you just can think of, okay, how my fiber should go, and just capture those curves or point clouds somehow. And then we can definitely help you write a script, or if you can import them right away, you have a winding pattern that is generated by your knowledge of composites manufacturing and then brought to life with AFP winding. So I think I already went through this. My So I think, as I said, so the folder that I'll be sharing will have the folding boom, um, the bracket that I shown earlier. It will have the fiber steering on tank. It will have definitely the hydrogen tank winding that I showed, the ISO grid structure. There's actually a selective reinforcement of the dome that I showed at the very beginning, and a tapered tube as well. So I actually wanted everyone to really, so anybody who is in this webinar, once you have the art path installed, just once you sign up for license, just drop me a message, so I know that you were in the webinar, so I can grant you the license, and then you can access all the files here with the, yeah, all the simulation data and everything like that in there. Okay, so I think this is more, now we are getting towards a conclusion in a way. where the benefit are, I think, a bit more obvious. But let's you're able to go not only in the convex sections of the winding but concave, and you can do all the paths that you want to follow. So, and I think, as I'm assuming everybody's aware, the filament winding, you're really dependent on friction and tension and how what is allowed. I don't know if it's allowed even to go below 20 degrees along the length. But then with this, there is no limits. As you saw with the isogrid structure, we did complete 0 degree passes, no problem. You can do thermoplastic winding, which I feel in today's day and age, it's a must have. With all the winding knowledge that is out there already, this is definitely a must. I think this is something I feel is there. I have not found the data for it, but I believe with the you have compaction pressure on, you're able to get much better consolidation compared to just the tension, and without losing the placement accuracy. I believe you can apply a lot more tension, and then kind of the tape can narrow a bit, because all the fiber try to come together and like try to bunch into one, and you end up creating like different issues. But with this scenario here, because you're pressuring it, you can apply much more tension and pressure together, and then you are able to achieve what I would call the best compaction possible for a part. And the digital twin, as I talked about, there is a lot of sensors that you can choose. We already like offer from our side, like there's a thermal camera, the thermal sensors, then there is line scanner for knowing, okay, how accurately things are placed compared to what I planned. So with all these sensors plus all the other like standard sensors, like how much compaction I'm applying, how much tension I'm applying at each location, basically you know a lot about your part, how you're building it up, and how you're building the quality into the part, not working at the post and trying to fix things. So it's really, really critical property to have going forward. Yeah. So let's see what I have found as the application for this AFP winding that is already out there, used, and but is not talked in the same terms. So the first, and I think one of the very prominent application, is the electric motors for Tesla Model S Plaid. So that's the highest rating electric car from the most the best electric car company you can say. And they use the overwrapping of continuous tape thermoplastics, just because it's able to make sleeve for the rotors that is extremely thin, and it's allowing a lot more benefit for them to be able to rotate motors at really high efficiency level. And I think this is like the killer application, if you would like to think it that way. But then yeah, there will be a lot of electric motors in our life going forward, and I think if you can be part of making component for the best electric motors out there, pretty good bet. Then I think this is something from GK and Fokker I saw, where they did this very unique kind of two beams in one geometry. This is basically a classic case where a filament winding will not work, but AFP winding will work, where you have a negative curvature, and then there is addition to it being thermoplastic. So you would have to have basically AFP winding for be able to achieve this part. And this is called floor beam in the fuselage frame, and this is, I think, part of the Clean Sky 2 project. Then isogrid structure. So there is, I think, few European Space Agency projects which have already used this tech for making the fairings to begin with, and then I believe now with the FPXS combined with winding, it's able to be permeated to more normal applications. So where you start to see it in cars. So we did like a roof of a car with the same tech. So there's a video on on our YouTube channel. Um, yeah, I think then we go to Type 5 hydrogen tanks. This is something I feel is already possible um, with filament winding, but the main drawback that comes with it is that you're trying to go towards a sustainable future, but the only way to dispose of this tank is to burn them. So that's where I think the thermoplastic Type 5 hydrogen tanks come in, and they definitely bring in like a lot more value that you're able to then get from it. So yeah, and they have definitely much better properties as well in terms of impact and rugged usage and repairability. So there is a lot more other than just the recyclability aspect to the Type 5 hydrogen tanks with thermoplastics. But that is, I believe, like definitely a growing set of application similar to EV uh, motors, but slightly I would say more at the moment in aerospace and flying taxi space. Then there are hydraulic composite cylinders. I've seen these. I would say these are more niche of application. But what if you go around and notice any of the cranes working in constructions, um, the ones that have to go really high, if they have metallic cylinders which has to hold a lot of pressure, they really struggle with this type of application. So this is why you would need an application that is able to just have the either thermoplastic. I think once again I am a bit more for thermoplastic, but it could be thermosets as well, or it could be any other resin. But I think there is the key benefit of having a lot of hoop windings in this, and then there is some actual windings to hold all the hoop windings together. So this is definitely a very very good application. Not the least, the last one is the combination that we can use with the 3D printing and AFP winding. So with once you start with using a robot with AFP winding, what you essentially have is a robot that can also support a printhead. And then with printhead, you're able to do, which is, I would say, robotic extruders' main application today is creating a mold. So you can actually, on the chuck, print your mold shape. It could be of whatever shape. Either you can use that as the mold, or you can reinforce it with AFP winding thermoplastics. And this is a bit more out of the blue in a way that it's a new set of application which I have not seen come out. I know few use cases that I cannot talk about, but I believe there could be a lot more once, like I think through this webinar or people thinking about these applications. Like, okay, yeah. So that way, I believe there is a hell lot of application that can be created in a very short period of time, just by combining these two technologies. So you have FP winding, and you have continuous fiber 3D printing, or just the 3D printer that works from the same robotic platform, has the access to the same chuck that is rotating in front of it, and is able to create mold at the wheel, and then just reinforcing it or using it as a mold. Yeah.
Praveen, we have one more question.
Yeah.
They're asking, I would like to ask, what will be the best way to demold the inner mantle for the hydrogen tank binding? The best way to demold the inner mantle for hydrogen tank.
So depends, to be honest, completely. If you're doing Type 5, I don't know any other way but then to use soluble or how collapsible mold. I have not seen good collapsibles mold out there. So there is this company, and this is just a plug for that company. I think they're called Aerospace Consultant out of Switzerland. They make this toolings which are soluble. So I think they are a good provider of this. So those are washable mold, basically. I would see, like, I don't see why not. You can 3D print a soluble mold as well, and then just wash it away. And if there is a way to capture that washed element and to reconvert it into, again, 3D printing raw material, so there is like a cycle to it. But yeah, I think those are the only ways. So I have done a few Type 5 tanks now, and I've done it on the washable molds. Unfortunately, that's the application that I know. And in my previous work, I used to, so for upper stages of launch vehicle, we used to have like a solid motor case, which was also built with winding application, and it is made from, once again, collapsible mold, which is sand, and that you can just break out. Don't have to wash it. Basically, you can just break it out, and then there is like a metal structure supporting it. So you can just fold that metal structure and pull it out. So there is the two approaches that I'm aware of. I hope that helps. Yeah.
Yeah,
Thanks for the question. Yeah.
we have one more. What is the
Okay.
highest winding tension you can apply with AFP winding?
Depends, actually. It's just a function of motor. So the standard system that we have applies 60 to 100 Newton. Yeah, which I believe for most applications quite enough. But if you want to apply more, I don't think so. Why not? You just need to put bigger motor. So just let us know if you have to apply more tension. I think the only application that I'm aware of where you would need more tension is the sleeves area. So yeah, you can add additional tensioning at the end, or at the bobbin level. That's where I would prefer it to be. It's more controllable and out of the way of the actual geometry. Yeah. Okay. So yeah, I think we are pretty much at the end of the talk at this point. So what I would just try to kind of summarize this with few words. So we start with very basic filament winding when it was invented, to now we went to AFP access. That then we understood, okay, AFP, good process, added few functionalities, but made it expensive. AFP access made it okay, similar to the cost of winding system. But now with AFP capable with software to do winding, what can we do? And that's we went into learning about AFP winding, like why. And then we have, I think, about 6 cases where I was like able to highlight, if this is the shape, AFP winding, and that's why. The key differentiators I talked about, and then yeah, the how, which is basically there's a software, and then yeah, you're able to do it. You need to know about your material, your processes, but yeah, pretty much you're able to scale the process to pretty much to the same degree, but not as high as just normal filament winding. And then, as I said, there is like about 7 ish, I think, different projects that we have created just for this webinar, related things, so that we will share. So those will be the hands-on practice that we'll talk about. Some of them I was able to show how you can play around with them. Then we talked about more real-life applications and benefits of this process. Yeah, I think at this point, what we have is more like a Q&A feedback time. So Devendra, if you can put the feedback form in the chat, I think would be great. So that way we can collect feedbacks. And if we have any further questions, even from you, Devendra, I think, yeah, please go
I
ahead.
have a rhetorical question regarding your previous question. Just a second. So Liu Yan asked, what is the highest winding tension you can apply, which you answered. But again, there is a rhetorical question. But rotor winding usually require around 500 Newton. Any advice?
Yeah. So I would not worry about like how much high tension I want, because it's just a function of like, okay, I just have slightly bigger brake. It does not break my bank to just have like slightly bigger motor. So I would say that system can be easily customized for up to 100, up to 1,000 Newton, like of braking torque, if that is what is needed, definitely. So with AFP winding, with thermoplastic winding, what I would go for is that the main takeaway is that you need to be able to control that tension well once you reach the end, and then you have your heat input very well controlled. Once again, because I'm talking about thermoplastic sleeves. So I think having that control is more critical than the actual how much tension value, because that is a very simple parameter that can be changed depending on the customer need. So it's something very very adjustable thing. So I would say, yeah, it should not be a worry or concern to go by. Yeah.
And one more question is there. If you're cutting the continuous fibers in between using AFP, the strength of the system won't reduce in case of high pressure hydrogen cylinders.
Yeah, so there is a very good study one of our friend did. So mainly, if you cut and feed again and restart, definitely it does not increase the strength. But what you're able to achieve, at the moment with winding, you have to complete your all the star pattern. So you have to go all around to able to achieve the angle and the actual thickness what you need for pressure resistant. But at the domes, you end up getting in certain areas, especially at the poles, very high thicknesses, which you don't need to have, because you have them because you want at the middle section of the tank certain thickness, but you don't have to actually go to the complete pole and you can cut. And there was a study that was, I think Sevitec has shown this in collaboration with, I'm just missing the name right now. But yeah, I think they showed that if you just reinforce the dome section, so as I showed in the video, if you just reinforce the dome, the amount of reinforcement that you need to put reduces by 35%. I'm pretty sure there is more space to improve that. But let's say if you are doing a tank with filament winding, to if you do it with AFP, I think you are able to achieve that much better performance. You definitely need to improve and iterate on the design. But yeah, I think that is what is possible. That is what the benefit the AFP winding brings in. Yeah, compared to the filament winding. I hope that was the question.
One more question. Have you tested mechanical property of thermoplastic composites that have gone through your in situ process versus press or autoclave processing? Sometimes the performance drop can be challenging.
Yes. So to be completely honest, we have not done in situ with our system. So it's extremely slow. So we tend to avoid it. So usually what we do is we go at relatively fast speed. So if you're using laser, we would go at 200, 250 millimeter per second, or with the flash lamp about 100, 150, depending on the matrix of the material. And then have a post consolidation step, which is like the post cure step that I talked about. Um, and the performance usually is better with slower speed. That is what my finding is. So yeah, we have tested it with different partners who are independently evaluating this. Yeah, components. Yeah.
Okay. I don't see any more question in the chat.
Okay. Awesome. I think then what we can do, we can definitely have, I think, if there's any particular questions, I think me and Dave and I think James, who's not able to join us today, all are here to just mainly focus on this question. But then we can close down the webinar at this point of time. I really thank everybody who's able to join in person. And I hope that you also join us for the next webinar. It will be coming soon in a month or two. Yeah, really thank you, and have a nice day.